this split is also not very common in many different kinds of cosmologies where there are cosmologies where this can't be done, but at least for us, we can split this into a pure time dependent. I can do a separation of variables and have a spatial part. So, so we have been focused on this time evolution, and we are now interested in this delta of x. We have to understand first that cosmological theories usually do not make any definite ab initio predictions about the exact delta x, okay, that we are expected to observe. So what is usually spoken about are statistical properties, which means that we actually think of this delta of x as a random quantity. It's actually a random field. So what do we mean by that? So the meaning of that is the following. So we believe that by some processes, some quantum processes at the very early universe, which there are sources of fluctuations, and these fluctuations took a certain form, as if they are one realization of a random process. So for example, when we throw a dice, we get one outcome. So that's one realization of a random process, which is throwing of the dice. So our realization of the universe is one possible realization of some underlying random process, which we really don't know, some early universe process. Somehow, some random process has generated for us a random field. So we have, now the key thing to understand is that we have one realization of the universe, right? We have only one universe at our disposal. And we have one realization of a random process in which we get one form of this delta of x. So the fact that it's a random process, it means that we are not interested in the exact form of the function, but as we shall see, we would be interested in statistical properties. Okay. Now, second important fact is that when we talk about homogeneous and isotropic universe, we talk about very large scales, right? We talk about scales which are of the order of 100 megaparsec or more. So on those large scales, we know that the universe is indeed homogeneous and isotropic. So there are no preferred positions, and you can't have a specific direction which stands out. So that is homogeneity and isotropy of space. The moment you have perturbations, so homogeneity and isotropy of the space is definitely broken. So you don't have homogeneity anymore, right? Because you have fluctuations. There is clumpy matter, and homogeneity is definitely broken. And of course, we saw that structure would not form unless these tiny inhomogeneities they grow and they form collapsed objects, right? So the point is that there are inhomogeneities which is definitely going to break homogeneity. Now there's another concept which is very crucial, that though the universe is no longer homogeneous, the statistical properties have a certain homogeneity. What it means is that though you don't have a constant density field everywhere, instead you have a fluctuating object, this delta, which is a random field, as I said. But what is important is that though you have these fluctuations, the statistical properties of these fluctuations, if you measure at different parts of the universe, at different points in space, they are not going to be different. So there is a homogeneity in the statistics. Okay. So this is, and same for isotropy. So there is statistical homogeneity and isotropy. So which means that the statistical properties of this fluctuating field, they don't have any preferred position. There is no preferred direction in the universe for that. So this is a different concept, completely different from the idea of homogeneity and isotropy. So now we are talking about statistical homogeneity and isotropy. So the concept of statistical homogeneity and isotropy, which has got nothing to do with homogeneity and isotropy. We are definitely talking about an inhomogeneous universe, but the statistical properties of delta, they have homogeneity. Okay. So as I said, there are two important points, that we have only one realization of the universe. So for example, we cannot ask the universe to give us a new value of delta. It's not a simulation where I can run it and get another delta, right? The real universe, we just have one of it. So we have one realization of the universe, and we have only one realization of the universe to test with anything that we make predictions for. So if we make any predictions for any statistics for this delta, we have to make it based on observations of one single universe. Now that you would say that is really crazy, because you are saying that delta is a outcome of a random process. So let me write that down. Delta X is a realization of a random process. So the question is, how, given one realization of the universe, how can we make any computation at all? Because we cannot have multiple realizations. So in probability, you know, right, to calculate, for example, statistical quantities like mean, standard deviation, correlations, etc., you need to have the different values of the random variables, and then you need the corresponding probability, and you find various averages, right? But the point is, here you have only one realization. You just can't have another universe to check stuff, right? So the question is, how shall we then make any predictions of statistics based on one realization of the universe? So that's an important question. Now, that problem is, of course, handled through the fact that we have two more assumptions, ergodicity and stationarity. So we'll come to that. But let me again reiterate what statistical homogeneity and isotropy means over here, that each realization delta X, I mean, we have only one relation, but any realization delta X, no matter what it is, will break will break the homogeneity and isotropy. But we shall emphasize that the statistical properties will not have any preferred origin or any preferred direction. Right. Now, to compute any average, you need basically, as I said, all these realizations, and you need a probability distribution for these different realizations, right? So that is how you compute average of any quantity. Or for example, if you have a random variable A and it takes values A1, A2, etc., and you have the corresponding probability P1, P2, and then you can compute the average value of A as a simple probability distribution. So what you need are these different possible realizations of A, and then you need their corresponding probabilities, and you can compute this. So what you really need to compute different statistical properties of delta would be all these different realizations of delta, right? Identical deltas which are generated by different as different realizations, and then you can compute that various statistical properties by looking at the probability distribution. So what you really need, so let's just diagrammatically talk about it. So let's say that this is my universe. I'm drawing it in 2D, but this is just the 3D. So what you need is that you need multiple realizations, right? You need multiple realizations, another realization, another realizations. You need all these realizations of the universe, and then at a given point in the universe, you have this delta, and then you can compute any function of delta, and you compute it for all these relations, and then you do some average. So you need all these relations. So this is like an ensemble of different universes which you need to really construct to construct this average. But this is impossible because we don't have these ensembles. Yeah, any question?
I am Devmalo Tapomoy.
Yeah.
So does the randomness imply that there is no any initial condition which will be followed by the perturbations, right?
So yeah, there would be some initial conditions in early universe, typically in inflation. So we believe that inflation processes, quantum processes in the inflationary epoch, they generate these perturbations. So there would be, but at the end of, I mean, the point where we start structure formation, we have to have seeds of perturbation, and these seeds of perturbation, which are believed for all our purposes, is basically one realization of some random process. So we have prescribed at some initial point some power spectrum. So no matter what you have, for example, what kind of, so we will define what a power spectrum is, some kind of a statistical quantity. So we have to say that, okay, I mean, there are all these processes which give rise to these fluctuations, but then we finally have one realization which we see, and all we can talk about is the statistics of that. So here our understanding is that we are not interested in what the delta is as a function of x. We are not interested in delta of x as a function of what kind of a shape it is. So what we are interested in is the fact that this is basically a quantity which is a fluctuating quantity, in the sense that it has values which are different at each point of x. And at each point of x, so if you fix a value of x, it's a number, which is basically the value of that number is the realization of a random process. So it's basically a random variable at every point. So it's a random field. So that's what the premise is. Okay. So the question is, now since we cannot have multiple realizations and you cannot have an ensemble of universes over which we can compute the average, what we need is basically the idea of ergodicity. So here the assumption is that universe is large enough such that different parts, so if you have a large enough universe, then different parts of the universe, if you partition your universe into, say, boxes, then each of these boxes can be thought of as if they are statistically independent realizations of the delta. So instead of seeing like a patch like this and considering an ensemble of that realization, we look at a big universe and say, okay, so different parts of this universe, they are as if independent statistical realizations of the same box. So this, I mean, it's the same universe. So what we are making a huge assumption. Instead of saying that I construct different random realizations and do this ensemble averaging for computation of any, yeah.
Sir, can we say this randomness is coming from initial quantum field fluctuations?
Yes. And we are not going to be interested in the source of the fluctuation of the randomness.
Sir, we are modeling our universe from the time of CMB formation, right? Because
even earlier, universe, even earlier.
It is also radiation dominated. So in our equations of treatment, and we should substitute also the term for this radiation.
Absolutely, very good point. Now we are looking at redshift for this particular 21 centimeter cosmology. If you do CMBR, of course you have to do radiation. I mean, radiation for electron radiation as a, in fact, coupled system you have to study. Now in early universe, when the universe is in radiation dominated epoch, I mean, say redshift greater than 10,000, of course you have to worry about radiation because that's a dominant component. And in fact, that analysis is entirely relativistic. You have to use full GR. So the equations for radiation would require a more rigorous relativistic computation. So there you would have photons, baryons forming a plasma, and then there's decoupling. So all that is there. Since we are deep into matter-dominated epoch, we are not really talking about the radiation has become dominant at the kind of epochs that we are talking about. So that's one reason we are not looking at radiation. But of course, in the primordial epoch, so we have cold dark matter is anyway always there, right? So since cold dark matter is what is primarily causing structure formation, which is what our interest is as of now, radiation would have a very important role to play in CMBR. It would also play a very important role because of its coupling with baryons. It will lead to something called baryon acoustic oscillations, which will manifest on dark matter clustering also. So all that is there. So if we get time, we can discuss a little bit of that, baryon acoustic oscillations, which is basically the same thing that you see in CMBR and anisotropies. But studying radiation would require full general relativistic treatment, which is not what we are doing in this course. So that, of course, that is done and that's very standard. So for CMBR physics, you have to do baryons, cold dark matter, and photons all together. That's so here we are not doing it for the simple reason that we are looking at low redshifts, and we are interested essentially the cold dark matter physics, which is creating these collapsed objects, and then baryons, as we saw, are treated as something which is following the dark matter. All right, that's one thing. Now, coming back to the source of these fluctuations, yeah, there are some early universe phenomenon. We are not interested, as we shall see why we are not interested, because finally there is only one quantity which all these early universe theories they would give us. It's something called the power spectrum, the initial power spectrum, and all that physics finally will get into the basically features of this power spectrum, right? And that is what we shall take from through radiation dominated era, then into matter dominated era, and then eventually into dark energy dominated. So the evolution will be then just something which is straightforward and standard. Not straightforward, but at least one can follow through it. Okay. So for our purpose, at kind of redshift that we're interested, we have a density field which is basically fluctuating, and at each point it is seen as a random field. Okay, it's a realization of a random field. Okay, great. So ergodicity would mean that we can this averaging over different volumes, which are partitions of one realization, would be the same. The expectation values that you compute using this would be the same as you would get by taking averages over an ensemble. So if you have a probability distribution of different realizations and you compute averages, you would get some number. And the same number is what you are expected to get if you do these kind of volume averages over different parts of the same universe, of the same realization. Okay, so that is the ergodicity. Now you can clearly see that there's a problem here. And this is a problem, of course, this would imply that another concept is actually crucial over here, that is stationarity, which means that when you look at the universe is not 2D, right? It's a 3D thing. The spatial, now it's a 3. So if this is the Z direction, then you can immediately see that along the Z, the universe is actually evolving. There's an evolution in the Z, right? On a given Z slice, you have one slice, but it's actually an evolution, right? So at each Z, because of cosmology, there's an evolution. And now the question is, if you look at this box, and you also have an assumption that statistical properties, if you wait for long enough, it doesn't change. If there's no change, that is definitely not going to be true, right? So when you apply this ergodicity in a box which has a big width in redshift, then there are severe problems, right? Then ergodicity is actually not going to hold, because there is evolutions of statistics might not be. There is no. So you need stationarity also. You don't want time evolution of these quantities, because otherwise, if things change, then this box cannot be used as using the ergodic hypothesis, right? So when you have a very large Z, you have to actually take into account the evolution and a departure from ergodicity and all that. But of course, let's say that, okay, we are not really looking at a box, we're looking at a slice, and then on a slice of a very small bandwidth observations, well, let's assume that we still have roughly some ergodicity, and we can use this principle to then compute expectation values. So finally, we are interested in expectation values or moments of this quantity delta, right? Which is, as I said, now random. Very good. So let's get a little bit more into this. So as I said, delta is a random function. So it's different in each realization, but we have got one realization. And let's, for the time being, let's say that, okay, let's say we have our universe.
Hello, Tapomoy. So I want to ask one question. So you told that so we have a big universe and we are then slicing it to game and saying that okay, these are independent such that we can consider them as independent realizations, right? So my question is, what is the typical size that we can assume for these small slices? Like, is there any size limit?
I'll come to that. It's a very good. So yeah. So basically, you want it to be. Universes. You basically want many real. If you try to do statistics, you would ideally want to have many samples over which you compute these expectation values, right? If you cannot do statistics with one realization, right? If you just get one realization, then you have just one number. Then what kind of statistics can you do? So ideally, you would want to do statistics or in which you need many realizations, right? So number of realizations that you get in that assuming ergodicity, would be dictated by what is the total field of view that you have, which means, say you are doing some surveys, you have some telescope, you observe the sky, and you observe in some depth and frequency. So your observation, say in radio observation of 21 centimeters, you basically say you probe this region of the universe. And that would be dictated by the kind of telescope that you use, right? Now, if you are doing some statistics and you want to do some expectation values, now if you're interested in scales, which are of the size of the entire box that you have, then, or anything that you are trying to measure has a feature which is of the size of the entire thing that you're observing, the entire universe that you're observing, then you won't get many realizations, right? Because if you're interested in observing a certain mode or certain feature which has variation which is of the size of this box, then you would get, say, just one realization or very few realizations. So your statistic would be encountering a lot of noise, right? So, so you would actually want, so depending on what you are probing, what scale you are probing, you would actually get that many possibles. For example, you're interested in something, a feature which is like, which has this kind of scale. So this kind of scale observations, you can see that this has, you can have actually many realizations, right? Because the kind of thing, the feature that you're observing is such a tiny thing that there are many boxes in which it fits. So to observe that feature, you get many ergodic realizations on which you can do the averaging. But if the thing that you're observing, which a feature that you're trying to observe is a large scale feature, then you get smaller and smaller number of realizations, and that introduces something which is called the sampling noise, because you are making an estimate of a statistical quantity based on very small number of samples, and that is what is called cosmic variance. So you must have heard that there is this thing called cosmic variance. Cosmic variance is basically error which comes because of the fact that you are calculating a power spectrum or a statistical quantity based on a very small number of samples. You don't have many samples over which you are computing the expectation. So depending on how you sample and how number of samples you get, you would have a noise. So that is typically what leads to an error. So answer to the question is, it depends on what scale that you're probing. So if you're probing a feature which is a small scale, you get many realizations, very good. And it's up to you and how many you want, because finally the number of realizations you get will determine what kind of noise you have, because finally you are making some estimate, right? You are making an estimate of a statistical quantity. You can choose whatever number of realizations you want to choose. That's up to you. Depending on that, you will get a certain noise. That is something you have to worry. You will get an additional variance because of the fact that you are not really doing good statistics.
If you choose a lot of realizations, then don't you think that the statistical independence would be compromised?
Yeah, you can't go arbitrarily small, but you are also interested in some feature, right? I mean, if you have a feature and the feature is not fitting into the size that you are really, you are probing some scale. You want to see something on a certain scale. You want a fluctuation of a certain size, right? Now, if you go into a box which is smaller than that, then you are not capturing that thing.
Yeah.
So that's actually meaningless. So you have to have at least something which fills that fluctuation, that wavelength, at least that. Right. No, so you cannot go arbitrarily small. And of course, and just give me a second, I'll discuss the point you just raised. I mean, what happens when you go very close? I mean, yeah, so let's do that and let's see what happens. So, and that's the reason why we are interested in going to the Fourier description. The entire thing that we spoke over here is in real space. Now you see, if I have, say, this density field and the over density field xt, and you can think of it like, okay, let me for simplicity, I just put this universe on a grid. So I have an ith grid point, and you have a value delta I, which is the value of this random field in the center of the grid. So let's discretize this delta. So this delta xt, let's forget t for the time being. You can just write this as delta I. So it's like a set, delta 1, delta 2. Now these are values at the center of the grid. Okay. Now we ask this question: what is the probability for this realization? So there's the capital N number of such grids. So this set is what you have. My question is, what is the probability of this particular realization of the density field? So you would basically need the joint probability distribution of all these numbers, right? So the question is probability of this set, delta 1, delta 2, delta 3, dot, 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 delta n is the question. Now, if I know this probability or have some idea about this probability, which we shall model, in fact, we'll model it in the simplest case as a Gaussian. So, I mean, Gaussian is always the God-given probability distribution. So you can take the default as Gaussian, and then we can look at deviations from Gaussianity. So that's what is traditionally done in cosmology. You start by assuming that this random field that we're talking about is basically the process. The random process is a Gaussian process. And then, of course, if it is a non-Gaussian process, then that would give rise to contributions. But to leading order, we will assume it's Gaussian. So this Fi, let us say Fi delta I is the probability of delta to be equal to delta I at x equal to I. And it's just a definition. And this could be a Gaussian. Okay, so it's a single variable and it's a Gaussian. Now, the crucial thing is, you cannot write this probability, which is probability of delta 1, delta 2, delta n. You cannot write it as basically a product of these Fi's. Because these deltas, because this is this delta, right? And this is a continuous field. These deltas over here, first the delta at I is correlated with all the deltas. Right? Because you pull that and the thing neighboring to it will also get pulled. So that all these, I mean, because of the fact that these are correlated, the probability, the joint probability of these deltas will actually not be the product of the individual probabilities. Okay, so that is the crucial thing. However, what we typically do is we go to Fourier space, and that's the good thing, because as I mentioned in the morning, that this Fourier modes in the linear theory, they're decoupled, so that you can think them of as independent. Different Fourier modes are independent, whereas delta is correlated. The Fourier modes delta k, then you go to the Fourier space. So let's do that. So we define this delta k. I think I use this capital delta. This is say delta x, and there's a 1 by v. This is in a box, right? So e to the power I k x d cube x, and you do this Fourier transform. So again, you have now this new variable. Again, this is a random variable, but now this is in Fourier space. So I write this as delta k, and this has again I, right? So this I is now in Fourier space. So this is ki is 2 pi by li, right? And in Fourier space, if you write this, the crucial thing that I want to talk about is that if you do this delta 1 tilde, delta 2 tilde, right? And this 1, 2, this is now in k, because we have gone into Fourier space. This will actually, these are all independent. So this will actually be the product of the probabilities G1 of delta 1 tilde times G2 of delta 2 tilde, and so on and so forth. So this is what I meant when I said that these different modes, they are independent, and they're statistically independent. So you can treat them separately. Okay, so that's a very important point. Okay, so we have made quite a number of assumptions here. So what is usually done is that these probability functions Fi, they are believed to be, I mean, they're in the, at least for standard cosmology, they're assumed to be a Gaussian.
So this, just a question. So this independence of mode is only for Gaussian field, or it can be for any field? This product
Here we have not made any assumption about Gaussianity.
Okay, so this is in general true for
this is just saying that they are statistically independent. Some probability distribution, they're independent.
Correct. Yeah, thanks.
So, but now we are saying that, okay, let's take the simplest probability distribution, which is the Gaussian. So then you have, you know what this is. It will be G, these quantities, this Gi of delta K tilde. I don't put a tilde there. I mean, I put a capital delta, so I don't need it. Tilde. Anyway, doesn't matter. You understand what it is. So this is basically e to the power some normalization, e to the power minus delta K squared by 2 sigma, and standard Gaussian. Okay, so we have to understand that we will study this probability distribution in the last lecture when we do halo mass function, etc. But for the time being, we have to understand that, well, we can do an analysis using these probability density functions, but there, what the analysis would require you to construct these multiple ensembles, and in each ensemble you have one realization and you compute expectation values using, say, probability distribution. So the moment we talk of an expectation value, one thing would be to compute its expectation value using probability distribution. So integral whatever quantity you say a, it's some a, and then you have f of a, right? So this is one way of doing it, but we are not going to follow this because this is not feasible in a universe observationally, because we don't have these multiple realizations. So how do we do it? So what we shall do is, as we said, we talk about using the volume average. So we are always going to this ensemble average will be for our purposes be replaced by a volume average, assuming ergodicity, assuming stationarity, of course, which are not going to be true if you have very large bandwidth observations, and assuming that this ergodic principle holds, we will actually use it. We can't prove it that this ergodic principle. There is no proof for it.
Hello.
Yes, question.
Can you repeat the thing, the independence concept of the independence things?
So the point is when you look at in real space and you look at this discretized, you can look at the grid and you have some density field delta. So then you can think of it as a discrete set of n values, which are the values of the density over density field at the center of these grid points, right? So my question is, what is the probability of this entire realization? So delta is the full thing, right? So that would be the joint probability distribution of all these deltas, of these small at each center. And this is not going to be the probability product of the individuals, because these deltas are correlated, right? Because you think of a fluctuating field, no? What does it look like? It looks like it's like a wave. It's going up and down. It's also a funny random field. Now, of course, they are correlated in the neighborhood, right? So, of course, these probabilities can. But when you go to Fourier space, then that delta is now broken up into this different k modes, and then you have this capital delta, and these are independent. So in Fourier space, if you now grid in Fourier space and you look at the joint probability distribution of these Fourier amplitudes, those probabilities will be in product. So there is no, these are uncorrelated. So they're statistically independent. That's what I meant. Is it clear?
Yeah.
Okay. So the first thing is that it's a Gaussian variable. So you can immediately expect that the expectation value of delta would be 0, right? It's a 0 mean. So I mean, that's the first thing. Okay, so what we are crucially, or even if it's offset, you can obviously subtract that out. But the point is, we are more interested in the higher order statistics, so in the variance and generalization of the variance, which is actually from the 1 point function, which is of course vanishing for a Gaussian field. But then we are interested in what is called a 2-point function. So again, we think that there's a box, and let's say there are 2 points, x1 and x2. And we are interested in this quantity. So we can take delta at x1, and we can keep the time, delta x2, the same time, equal time. So it's basically product of the delta at these 2 points, and it's just what it means. It's a correlation. It's a product of these two. So this quantity is what we call xi, and it depends on x1, x2, and t.
Excuse me, shall I interrupt?
Yes.
Hello? Okay,
yes.
So when we say that in the Fourier space, the modes are not coupled or modes are not correlated. So this is a feature of a Gaussian field, right?
Yeah. So I mean, yeah, under linear. So basically, it's under linear transformations for a
Yeah, if you have bispectrum, etc., then you will have contribution from there.
Right. So the 2-point function is the, yeah. So the 2-point function is what is the only thing that you have is basically the 2-point function, because everything else can be written in terms of that. That's correct.
Yes.
Yeah. So we are basically assuming Gaussianity all through here.
Are there any non-Gaussian fields which are statistically independent?
You would need more higher order. So the correlation that, so it's, I mean, what do you mean by you would need, say, for example, the Gauss, this is a delta is a Gaussian field. So for a Gaussian field, the correlation, the 2-point correlation function is all any higher order correlation. So if you have the 3-point function or things like that, they can all be expressed in terms of property of a Gaussian field is that any higher order correlations can be always expressed in terms of 2-point functions.
Correct.
And that is something which will not hold for non-Gaussian. So you would have
That means,
all possible correlators will show up: 2-point, 3-point, 4-point, 6-point, everything.
So whenever we say statistically independent, we always mean that it's a Gaussian field, right? Or
statistical independence is something which we need to compute these expectation values. Okay. Unless you have statistical independence of one realization with respect to other, there's no meaning to construct an expectation value. So you have whatever is within the brackets, these angular brackets, whatever that is there, you need another realization of that. So you need another independent realization of that. Correct. Right? So that is what we are talking about. So that you need. Otherwise, there is no meaning to compute these expectation values, right?
Correct.
So that you have to keep in mind. Now we are not doing it over an ensemble, we are doing it over a volume. So and that is where ergodicity comes in.
Correct.
So that is an assumption, and we are going to take that as an assumption. I mean, it is in fact not accurate. As I said, there are many situations where ergodicity is broken, and we have to tackle it as and when. But largely speaking, we'll assume this ergodic principle holds, and whatever is within the angular bracket, this average is computed, has to be computed over different realizations of it. But here we are assuming that this average is done over the quantity within brackets calculated at different points, at different parts of the space. So that's what I'm talking about. So it's basically the volume average is replacing the ensemble average.
Correct.
And that statement is what is meant by ergodicity. So when I say that, okay, so let me explain here. So when I put this angular brackets and I write this, what it means is that I have to compute this delta at x1 and x2 and find this expectation value. But the crucial thing is that this quantity, as you can clearly see, will have a slight problem, because we just said that this is going to be sensitive to where x1 and x2 is, isn't it? As you can see, it's a function of x1 and x2. But that will break the idea that we at the very beginning introduced, which is statistical homogeneity. There's also this assumption that statistical quantities, they don't have any specific choice. I mean, they are not going to be sensitive to where we are computing it. So if we translate the whole thing by some constant, the thing should be the same. So you can just translate delta x1 by some y, and then similarly delta x2 with some another added some y, and this should give the same thing. It should give exactly delta x1 t, delta x2 t. So which means that if you add a constant to each of these positions, and it's basically translational invariant, so it immediately means that this xi which you have must be dependent on the difference of these two, right? Because this constant addition will then not affect it. So xi will actually has to be a function of x1 minus x2. And this is just pure translational invariance. I'm asserting translation invariance of the correlation by imposing the fact that there is statistical homogeneity, because this quantity should not depend on where I'm measuring it. And exactly by the same token, since x1 minus x2 is a vectorial quantity, right? So it has a direction. So I can immediately again impose that, okay, I mean, if there is statistical isotropy, there should not be any unique direction. So then this xi should also be just dependent on the instead of the direction, just the magnitude of this. So from statistical homogeneity and isotropy, we are expecting that this correlation function should depend not only on the difference, but the magnitude of the difference of the 2 points, right? So now you see, this actually makes sense how to compute this. So what you essentially have to do is So this x1 minus x2 is some s, and it's just a scalar because it's just the distance between 2 points. So this xi is a function of s and t, where s is the magnitude of this. So what you really have to do is take your box, your universe, and take any 2 points which are separated by s. So take any 2 points which are separated by s, and you compute this. You multiply, you take the product, and you take the average. So you put a stick of length s, and you put it all over this box, wherever, and you compute this xi by multiplying the value of delta at the 2 points, and then you get the xi. So see, now you see how this ergodicity is at work. So instead of doing an average over ensemble, we are actually doing this volume average, and statistical homogeneity and isotropy tells us how to do it. Now the thing is, here comes the real problem. So if this S is large, right? So if you have a very large stick, then you won't get many realizations, because it will fit the box almost. You would have very few realizations, and the number of samples over which you make that average will be much smaller. So that will introduce what is called, what I mentioned as the cosmic variance. So using ergodicity, we estimate the xi of st, the correlation function st, from a single realization by averaging over all pairs of points that are separated by s, right? Instead of doing that ensemble average. This is reasonably going to give you a good answer, provided you can immediately tell when it's going to give a good answer when s is much, much less than L. If L is the box size and s is much, much less than L, you would have a reasonable statistics that you can do, and you will get a good estimate. Now, of course, I mean, how much small? Well, you can take a very small box. Well, it will contribute to a big noise, what is called the sample variance noise. Very good. So try to understand, we are trying to estimate this quantity from a given box, and what it amounts to. Yeah, question.
Yeah. Can you explain the problem of stationarity here in this context? So are we taking same time because of that?
Yeah. Stationarity would imply that the statistical properties don't change with time.
Yeah.
Now, if you have an evolving universe on a given slice, it's fine. But the next slice, there's a cosmology, right? So everything has evolved. So the box has one direction in which things are changing. So if you're saying that the long-term behavior, I mean, the time direction and one of the spatial directions, right? In cosmology, the redshift direction, which is also time, is also the radial direction, isn't it? And that's where the problem is. So there is an evolution there.
Yeah, you can understand time, but how is one of the space dimension, how is it changing? Like, what is special about that dimension?
No, right. So the point is, you measure in redshift.
Yeah.
You measure different slices at different redshifts, right?
Yeah.
And at a given redshift, you can think of it as a distance, right? So you take a redshift and you think of it as some distance from you. So you have a sky, you have a plane of the sky, and then you at a given redshift, and then you change the redshift, you have another slice. So different redshifts corresponds to different slices.
Yeah.
Right. So how do you see the cube of? So you have the theta phi on the sky, and you have z. Right. But this is the direction in which the universe is evolving, isn't it?
Yes, but that is okay in the case of CMB, etc. But I'm just thinking for like if I have a cluster of galaxies,
it's not a CMBR it's perfectly fine, because CMBR doesn't even, CMBR is just one surface. It's just theta and phi space, all you have, because it's the last scattering surface that you're observing. There is no there is no z at all. That's a big difference from the CMBR observations to 21 centimeter observations, where your observation is the data is in the form of a 3D. It's a 3-dimensional box. CMBR data is in the form of a 2D box, a 2D surface, because it's only theta and phi, right? It's the last scattering surface. The crucial difference, and that's why it is called tomography, right? Because you can actually do tomographic imaging of the universe by tuning the redshift. By tuning the observing frequency, you can actually probe different redshifts, right? So you not only have the information of the density field on the sky, on the theta phi, and you have also the information along the redshift direction. So that's what makes it but that's also the cosmological evolution direction. So statistical ergodicity that we talked about is a big problem. So people talk about light cone effect and all these things. So when you have large bandwidth observations, you have to take into account evolutions of all the quantities. So it's likely, but if you're working on a surface and you're working with a very thin delta Z, it's reasonably fine.
May I add something? So the next lecture is on the light cone effect and this line of sight effect basically. So
oh, very good. Kanan is going to talk about.
Kanan is going to.
So Kanan and many others, they've actually worked on this problem that when you do this analysis of a box, you really don't have the Fourier space, because these three directions are not equivalent, right? We use it as a three, I mean, mathematically we write it, but this third direction is something which you have to worry about. So you have to
just to
basically
make
do
it
something.
clear, can I ask another question? So is the same thing applicable in galaxy surveys also?
Yeah, but for 21 centimeters, the bandwidth is much, much larger, right? Galaxies are still in a slice. So if you have very deep surveys, very, very big bandwidth, yeah, you have to worry about it. But here it is crucially important, this light cone effect.
Sure. Okay.
So for 21 centimeters, you have to worry about it because you are essentially talking about very large bandwidth observations.
Okay.
So ergodicity will be an issue and that will be addressed. So I think people will talk about it.
Okay, sure. Thank you.
Okay. So it's perfectly fine to do it on the theta phi. So you can do what is called an angular power spectrum. But then how to tackle this delta Z direction? Do we really talk, do we just keep it as a correlation function? Do we actually, how do we Fourier transform in that Z direction? It's a non-trivial problem. So I think Kanan will talk about it. So the details you can discuss with him. Okay, great. So let's go back to our definition. So we have this xi, which is a function of S and T, and S is just the distance. And this we saw is just delta x1t delta x2t. So let's now go to the Fourier space description of this. So first of all, one thing we should understand, delta is real. It's an actual density field, right? So delta is real. So since delta is real, what can we say about delta k? So delta x is real. So what can we say about delta k? Do you know this relationship of delta and delta k, and what the reality of a quantity? What does it mean for the Fourier transform? So it's very simple. You write the definition. So what you can show is that delta k will be actually same as delta star of minus k. That just follows from the fact that this little delta, the real space quantity, is real. This is very important. Okay, good. So since it's real, I could have very well written a star. It doesn't matter. Okay. So if you do that, we can write the whole thing in terms of the Fourier transforms. So let's do that. So the expectation quantity. So now these angular brackets would always mean some volume average. Okay. And then you can write the first as some d cube k 2 pi cube e to the power I k dot x1 delta x1. Let me just forget the time for the present, because that time is just a capital D multiplying. Okay? So that we don't have to worry. And from the second, you have another integral d cube k prime 2 pi cube. And I could just have taken star. Doesn't matter because it's real. So here you would have it to the minus ik x2. And you have a, oh, what have I written? This is delta k. People should have stopped me. This is delta k. And this would be delta star k prime. Right? So if you collect the terms, what you get, there'll be two integrals. So this angular average is sitting. So you have these two integrals d cube k prime. That's 2 pi to the power 6. Then you have e to the power I k dot x1 minus k prime dot x2, and then this delta k, delta star k prime, and angular bracket close. Now you see these are all known functions. The statistics, the random stuff is over here. So the angular bracket can be shifted there, the integral. So the integral can be just kept as it is, and you can push this angular stuff over here. So d cube k prime 2 pi 6 e to the power I k dot x1 minus k prime dot x2. And this is this quantity delta k delta star k prime. Very good. So what we are writing is basically the xi st, but now we have written it in terms of all these Fourier space quantities. So we know that if we make a translation, so this is basically xi of, as I said, x1 and x2. So if you just translate every x1 and x2 so if you just change x1 to x1 plus y and x2 to x2 plus y, then the same quantity would now be this integral d cube k d cube k prime 2 pi 6. This thing will remain e to the power I k dot x1 minus k prime dot x2, and then you have
You are mute, Tapomoy, you are mute. Can you unmute?
Can you hear me?
Yes.
Okay. So for it must vanish, the integral must vanish for k not equals to k prime. And thereby we have to impose that, right? So we have this thing cannot depend on y.
Tapomoy, can you repeat the last few minutes, because
So okay.
everyone missed. Yeah, it's
This
still
y
not.
hangs around over here. Can you hear me?
Yes, now.
Is the screen visible?
Yes, yes.
Okay. So this integral cannot depend on y. This entire thing cannot depend on y. So that is completely fine when k is equals to k prime. So that is fine when k equals to k prime. But when k not equals to k prime, this thing will always survive. So this integral will depend on y. So the integral must vanish for k not equals to k prime. So what we do is we have this, right? So we have to impose that condition, so that it's something that integral must vanish for k not equals to k prime. So we introduce a delta function. So we define now delta k, delta star k prime equals to, and this is now a definition, 2 pi cube, something called p k delta. This is Dirac delta k minus k prime. So once you have that, you will immediately see that you will have this Dirac delta will now come in. It will ensure that this y thing disappears because k has to be equal to k prime. One of the k integrals, if you do, then you basically have the left hand side was xi of st. Now you would have essentially d cube k 2 pi cube e to the power I k, because now it is just k1 and k prime are the same, so it's just k dot s. S is the difference x1 minus x2 and pk. Great. So this quantity pk is what we call the power spectrum. So as you can see, it's a Fourier transform of the correlation function, but it's not so straightforward where it comes from. So I have to go through all the steps. So of course we have not. So we should, since I'm putting this t over here, I should put a t over here. But you can immediately see what the time dependence would be. The time dependence would be just a d square or d plus square because it's a growing mode. And then it's just for the deltas. So it's just d cube k 2 pi cube e to the power I k dot s. So that's the definition of the power spectrum, which is of one of the most crucial things that you will study in this series of lectures, because for 21 centimeters, we are doing everything for dark matter, but then at the end of it, you will finally see that today you saw Somnath talk about the optical depth of 21 centimeters, which, if you remember, was proportional to the number density of neutral hydrogen, and which would be related to the baryon density, and then eventually related to the dark matter over density. And finally, we'll calculate the power spectrum of the 21 centimeter brightness temperature, which through all those variable change finally would be related to the dark matter power spectrum. So finally, the crucial thing of interest for us would be measuring this power spectrum, and via, of course, the 21 centimeter power spectrum. So I think, yeah.
So pk, so the k dependence on p can,
yes,
is it isotropic or it can?
It is isotropic.
It is always isotropic.
Yeah, unless you have some peculiar velocity or things like that.
No, I mean whatever you are doing here. So
Yeah.
that vector in top of k, where does that vector goes away in the calculation?
That is again your statistical isotropy, right? I mean, you can keep the vector, but there would be statistical isotropy. There's going to be this pk would eventually, if it's anisotropic, that would mean there is some direction, right?
Yeah, so then volume average will not work.
No, that is okay. I'm just wondering.
So right now you can retain. I don't have a problem in retaining a k with a vector. Same, it will turn out that there is no directionality, right? So pk will be a function of k.
Yeah. No,
because otherwise it would give. I mean, finally, this is going to be coming from primordial power spectrum. So that would mean primordially you have some direction.
No, I was just wondering the analysis that you have done. So it takes care of the vector sign of S, but does it anyhow take care of the vector sign?
It did not really take care. You see, I have just said it.
No.
I have just asserted that it should be a function.
Right. You said that it is a function, but
yeah. So here also I'm saying it is a function of. I mean, I'm imposing by hand statistical isotropy. Let me put it this way.
Okay.
Because there is nothing in it. See, this xi, if you impose statistical homogeneity, then it should be a difference. But then it can depend on the vector, right? x1 minus x2. Now I'm saying that it won't have a vector, so it will be just that.
No, but if you do not consider it to be x1 minus x2, then you cannot arrive at the power spectrum and xi relation.
No, that is correct. So the translation invariance is there, but translational invariance does not necessarily imply that it would be dependent only on the magnitude of the distance, right?
Right. So the isotropy argument can be done at the last stage also. I mean,
It can be done at the last. I could have retained S vector over here.
Right.
Psi as
Okay.
Yeah, that's correct. That is correct. That is true. Yeah. So it will turn out that yeah. So okay, good. So this is going to be the beginning of a lot of things. In fact, this is I think in structure formation, this is the most important. But of course, we don't know what this. I mean, I've written something as power spectrum, but I mean, somebody would say, but you don't know anything about these capital deltas at all. You said these are some fluctuating fields, some Gaussian random process and things like that. And what is this power spectrum? I've just written this ensemble average, which is something you should be computing using some volume average. You can compute it, of course. If I give you a density field, you can always compute it. You take the Fourier transform of the density field and you compute this. I mean, that is what I think many people compute. But
when you are saying is volume, you are replacing the ensemble average with volume average, then you cannot keep the vector sign, right?
No.
Yes.
No.
So
I mean, the vector sign is not going to be there. That is statistical.
Yes,
I'm just
because you are replacing with the volume means there is no preferred direction. Like
right.
Each axis is same.
Yeah. Right. So that homogeneity isotropy argument.
No, I didn't get. See.
So what he's trying to say that there is this in K space there has to be spherical symmetry in the sense that there is no theta dependence, right? This PK, this P can depend on K, theta, and phi, right?
No, but so that was my question. But why volume average requires that? Volume average
because it's a volume, means you cannot be direction dependent. So it's
no,
volume,
I mean, volume average is not the issue. The volume average is not the issue. The issue is the fact that you are your average.
So let us say that I have a field which is not statistically isotropic but homogeneous. Okay, so in that case, can you write the last expression with a vector sign on S because K already have vector sign?
I mean, the 21 centimeter signal is that way. Finally, the 21 centimeter signal has anisotropy.
So you can write the last expression.
21 centimeter signal is P as a function of K, and it has anisotropy K and mu. It is actually anisotropic. It has and the power spectrum is some P of K, but it can be split. It is some function of K and then some function of mu, some cos theta. So it can be anisotropic, of course. So that is possible, right? Due to redshift space distortion, you know that if you measure things in redshift, you would have an anisotropy. Your homogeneous density field, I mean, will actually have isotropic field will actually have an anisotropy because of peculiar velocity. It will appear. So that will appear as an anisotropic contribution in your power spectrum. So that is not an issue. That is actually not an issue. So Rajesh's point is
yeah, for 21 centimeter.
Hi, Prasun. This is Kanan.
Yes, sorry.
Yeah, no. So I think the discussion that you are doing it now. I think you can keep vector sign in PK as well as in Xi. So you can write vector sign.
Yes.
In principle, yeah.
If you know that you have statistical isotropy, then the vector sign, it will not depend on it. But if there is anisotropy, then it will be dependent on that direction. So it is possible. Okay, so I think I'll stop here. Kanan is also here. I think it's good time. I think Kanan can talk a little bit about light cone and breaking of ergodicity because a lot of people had questions on that. So time evolution along Z, and so I think you would talk about it, right? A little bit.
Not in detail, but I will touch upon those.
Okay.
Yeah.
Good. So fine. So I think it's a good time to stop. Tomorrow we will do a little more of this. So we'll try to see what this power spectrum is, and we will see what the primordial power spectrum is and how we can come to the present day power spectrum from there. And then we will look at, of course, the power spectrum and its normalization and things like this. We'll focus some time on power spectrum. And then we will go for the next next two lectures, I think that I have, I think tomorrow and the day after. What I'll do is I'll do some nonlinear. So I will do a little bit of quasi-nonlinear theory, Zeldovich approximations, and the spherical collapse and halo formation. So I will, I think from tomorrow onwards, we'll slowly go to nonlinear structure formation. So after a discussion on the power spectrum. So yeah, over to Kanan. So I will conclude now.
Okay, thanks, Tapomoy. So we'll have our